In the MCR, the room that we were in, the main control room. Why is it so quiet in here?
Actually, that's a really good thing that it's quiet in here. We try as much as possible to make things automated, streamlined, efficient. So if things are quiet, that means that everything's going well. It's when this room gets busy that you begin to worry, because that means that the spacecraft, like any toddler, has thrown a tantrum, and they do from time to time. And then the various engineers and people will come in here and work through the problem, troubleshoot it, and get the spacecraft back on its feet and doing what it's meant to do. But the fact that it's just Tim here today is a good sign that the other 3 missions are quietly waiting their new friend in space.
Yeah, so the 4 missions from this room, hopefully from the when will they take control in this room? Do you know?
So it'll be a few days. We do all the most critical activities first of all in the main control room, where we've got everyone in there ready to jump in at a moment's notice, all, as you saw, linked up so that we can talk to each other and discuss and work problems very, very quickly. Once we're satisfied that the primary bits of getting the spacecraft safe and stable are done, then we move from that room into here, and then starts a fairly intense process called commissioning, which lasts over months, where we go from something that's just stable to something that's really ready to do its mission. And that's a lot of hard work, but also very interesting.
Yeah, so you've worked here for 18 years, so would you encourage other people to come and
Yes.
work here?
I mean, absolutely. You can probably hear it in my voice. I absolutely love it. I mean, when they told me I was given the opportunity to fly spacecraft, I was jumped at the chance, and I'm not going
to... Next time I'm here, I need you to show me where they keep the stash of tea. That's my only problem.
Yeah, we have multiple stashes. It's all about redundancy and backups here.
Yeah,
so,
no, I've not found the tea yet. Thank you very much, Thomas. Always a pleasure to chat with you. We're going to have a closer look now at the Euclid mission and the purpose of the mission. So we're going to have a look at that on a video right now.
The universe is not what it appears to be. Visible stars and galaxies make up less than 5% of its total matter and energy. The rest consists of mysterious, invisible substances called dark matter and dark energy. ESA's Euclid Space Telescope is a mission to investigate this dark side of the universe. A display of innovative engineering, the 4.7 meters tall spacecraft carries 2 instruments that will examine visible and infrared light from distant galaxies. It's taken more than 3,500 people in 21 countries, working in more than 300 institutions and 80 companies to make Euclid a reality. This extraordinary telescope will observe around 6 billion galaxies, creating a 3D map of the universe, spanning the last 10 billion years of cosmic history. The shapes of the galaxies and their distribution across the universe provide vital clues about the nature and behaviour of the dark matter and dark energy. Analysing Euclid's data will allow us to see the universe not like it appears, but more like it really is.
So I'm delighted to be joined by 2 of these brilliant minds that I promised earlier on, who were instrumental in this mission. That's Elsa Montagnol, the head of Mission Operations Division, and Eleanor Mariano, who are the spacecraft engineering manager for the Euclid project. Welcome to the broadcast. I'm going to start with you first, Elsa. The whole mission is about unravelling the mysteries of the dark universe. Exactly what on earth does that mean?
Well, this requires a comprehensive study of the composition and evolution of the universe. And in order to do that, the mission will generate the largest, most accurate map of the universe ever produced, recording the distribution of galaxies in space and in time, looking at 10 billion years of cosmic time. This sounds like a lot. Mm-hmm. And this will help us understand the nature and the characteristic of dark matter and dark energy, which form 95% of the cosmos.
Yeah, 3D map that goes all the way back in time as well as being a map. Yeah, it was really amazing. So Alina, how on earth do you build a spacecraft that comes close to fulfilling that mission?
Yeah, so the most important part of the mission and is inside the telescope. We have the 2 instruments, the NISP that is working in the near infrared and the VIS that is working in the visible, that during the observation will acquire a huge amount of data and images that hopefully will help the scientists to try to understand which is the nature and the structure of the dark energy and the dark matter. As I said, the two instruments are housed inside the telescope with all the optics that are needed for the observation. We have also the service module that is the platform that is hosting the onboard computer, that is somehow the brain where the onboard software and the OCS software are running. The communication system, including the antenna for the communication with Earth and the transfer of all this data to Earth, and all the equipment that are in charge of the attitude and orbit control. So there are a common effort, of course. The core, the heart and the eyes of the mission are within the telescope, and somehow the control and the brain is in the platform.
Yeah, I mean, it's so much to have to pack into a spacecraft, but we've just been seeing images of the spacecraft just behind you. It's a beautiful looking spacecraft as well.
Yeah.
You've managed to make it look good as well as perform as well.
Yeah, for sure, it's beautiful.
I'm going to get you back as well in the later parts of the program to go over how you actually really did get to build this spacecraft, because it's an amazing story as well. In the meantime, I'm going to ask people to come in with their questions. I'm asking questions, but you can join in at home too. So right from the comfort of your sofas, by sending me your questions using the social media and the hashtag #AskEaster, you can actually get these experts and many more as the program unfolds to answer those questions. So I've already had one. This is a question from Astros02231. Hi, Astros02231 on Twitter. This is a really simple one. Elsa, what's the reason behind the name Euclid?
That's a very good question. The mission is named after the Greek mathematician Euclid, who lived 300 years before Christ. He's the founder of geometry, and as this mission will look at the geometry in the universe, we felt it fitted to give his name to our mission.
Yeah, it's often with these things it's an acronym, but this time not. This time it's just about Euclid himself. Yeah, the geometry of the universe being the really important bit. That's what this dark matter, dark energy. We can't find out what it is without that geometry. Yeah, right. And people have been joking, I've seen online, about it being. It may find that it's non-Euclidean or something like that, but let's not worry about it. So, yeah. So. Thanks so much for joining us, Elsa. Eleanor, we're going to get you back as well. So, so we're going to get you back when we get to when we talk about building the spacecraft. So this is a major milestone of the mission that we're going to be talking about for the first time after launch, and that is the acquisition of signal. That's what we're going to wait for. That is our milestone for today. So our next guest is going to play a major role in making that happen, getting that signal from the spacecraft. And through the wonders of technology, we're going to go over and talk to them. They're the other side of the globe, way over in Australia. So let's see if we can get Susie Jackson, the manager of the New Norcia ground station, on the line. Hi, Susie. Welcome to the broadcast. I can see an absolutely beautiful dish behind you. So tell me how it is involved in the mission, and did you have to do anything special to prepare for Euclid?
Yes, g'day. So as you can see, New Norcia 1's behind me. That's a 35-metre antenna that we'll be using tonight to acquire Euclid. This is actually a reasonably routine support for us tonight. Of course, there's a little bit more stress involved because it's the first acquisition for a spacecraft. So we'll be running this one with both New Norcia 1 behind me and also New Norcia 2, which is up on the hill, which is a small acquisition aid antenna, a 4.5-metre antenna, to make sure that make sure absolutely that we get the signal from Euclid as soon as it turns on.
So how are you able to give, can you give us a rundown of how you actually track the spacecraft?
Yeah, so we start off using a wide beam antenna at New Norcia 2. So we're never quite exactly sure where the spacecraft is as it comes over the horizon. So we use an antenna that's got a nice wide beam in order to capture the signal from the spacecraft. At first, we're expecting the acquisition to be about 10,000 kilometres distant to us, which is in our book is extremely close. So we can use the small antenna that has a very large pattern, so we're able to see the spacecraft even if it's a little bit off course. And then once we've zeroed in on the spacecraft, we track in on the actual signal that the spacecraft is transmitting to us, and we're able to lock onto that, and then we're able to steer the large antenna behind me to get the very high gain on the spacecraft.
So it looks a very heavy dish, Susie. So how on earth do you move something like that?
It's actually the motors that drive it are actually only about yay long. They're actually quite small. It has very big gearboxes though, and the antenna is able to move. Unfortunately, you'll probably be talking to others when we move down initial acquisition setting. It's actually able to move at a whole degree from one side of the or one horizon all the way to the other 5 or 6 minutes. It's very fast when it gets moving. It's fantastic to watch.
Thank you, Susie, so much. But hang around because we're going to come back to you for more updates as we make our way through the mission. So good luck, Susie. So I've been joined here in the astronomy control room by none other than Pierre Ferrou, who is the mission manager. Sorry for butchering your name again. Welcome to the show, Pierre.
Thank you very much.
All right. So we've seen that this is like an enormous mission, and obviously there's so much involved with this. So can you talk about some of the sort of collaborations that you've had to make this happen?
Yeah, it takes a very strong, diverse team actually to build Euclid, and I can start with industry. The prime contractor, Thales Alenia Space, they have gathered a team of companies, many European industrial companies, and this team has basically built Euclid. We are talking about 140 industrial contracts. And a completely different type of collaboration and very strong partnership is the Euclid Consortium. So it's a network of institutes, agencies, and they have delivered the Euclid instruments, and they are at the core of the processing, the analysis, the scientific exploitation of Euclid data. They have basically set up a network of data centers. And one last type of collaboration, we are actually collaborating on Euclid with NASA, because NASA is providing some key pieces of hardware. They are providing one of these famous data centers, and also, of course, they are funding supporting scientists, US scientists, who work together with the European scientists to achieve Euclid goals. So as you see, it's really teamwork, and we are quite proud to say sometimes that collaboration partnerships, they are in the DNA of the European agency, and we are quite proud of that.
Yeah, absolutely. Yeah, you always see these big missions, lots of collaboration. It's fantastic to see. And talking of collaborations as well, we know that it's not a sort of one-size-fits-all for launch vehicles. You know, just getting this thing into space, it isn't actually easy. And for this launch, we've got a Falcon 9 by SpaceX. So tell us a little bit about why that particular rocket was chosen.
Yeah, it was chosen in a second time because we had to change rocket. And you have to realize that changing rocket for a satellite like Euclid, it's not easy. And what happened is that after Russia's war on Ukraine, we had to find a new rocket. And we looked for a rocket that would be compatible with Euclid, would be available so to launch in 2023. And after careful consideration, we selected Falcon 9. It was actually meeting all our needs. And the thing I would like to emphasize, and I think it's quite important, is to realize it's a difficult task to swap rockets. And our project team, the teams here in the Operation Center, industry, and SpaceX, they managed in less than 1 year to do all the checks, all the preparatory work that led us to today, with Falcon 9, with Euclid on board on the launch pad.
Yeah, I mean, this thing took such a long time to build, and then suddenly you're changing rocket. And yeah, I think it's an absolute testimony. I hear it a lot that you know, that's been an amazing piece of work, a proper solid piece of work. It's really good to hear, isn't it? Thanks so much, Pierre. Well, I think what we're gonna do is have a quick look on the activity in the main control room now and see what they're up to. Tiago, how's it looking in there?
Matt, so now we're in a bit of a waiting period.
Stay.
Waiting for the rocket to go, hoping for a beautiful launch, but the team now is waiting for the launch. And that's it from the MCR. Over to you, Matt.
So if you've just joined us, we are following the Euclid spacecraft launch, starting its million-mile journey to L2. There'll be more on L2 later on. I'll promise I'll tell you what that is. We're in the European Space Operations Centre, where the fleet of European satellites are flown and controlled by a large multinational team of scientists and engineers. We're going to go over to SpaceX when their broadcast actually starts. So I'm going to carry on talking to Pierre just for a little bit, and then when SpaceX are ready, we'll go over to them. So Pierre, if someone wanted to do your job, what would be your what would you say? What would you say to to some young student somewhere?
I think go for it because I've been working in ESA for more than 10 years now, and I'm still not bored about it. And really being in places like that now, we are launching a mission. I will be working on this mission for the coming years. It's just fantastic. Meaning it's just a dream job, and I just encourage people to go for it.
Yeah, and you're quite new to the Euclid project.
Yes, only 1 year, and we are talking about missions where some people have worked more than 10 years, 15 years on it. But still, for me, 1 year, and I'm already excited about the mission. Huh?
Yeah. So I mean, what did you do before? Did you do any exciting missions before Euclid?
Yes, I was at ESA, I was on Webb, so only 1 year ago. And basically, it's very exciting to see Euclid, which is going to be really a survey mission. We are going to map 1/3 of the sky, up to 10 billion years in the past.
Okay.
It's just...
So we're going over to SpaceX now, and so now is the start of the launch coverage, and we will be back in the lulls of the launch period, so to give you the science of the mission and talk to some people.
Deployed, and Falcon 9 has landed.
Hello, everyone, and thanks for joining us for our launch today. Falcon 9 is set to lift off from Space Launch Complex 40 in Florida just under 17 minutes from now. Our 243rd overall mission to date and our 44th mission of the year. My name is Jessie Anderson, and I'm an Integration and Test Engineering Manager here at SpaceX. And today we have a really cool payload on board the second stage. We're sending a space telescope for the European Space Agency to a Sun-Earth L2 transfer orbit, also known as the Sun-Earth Lagrange Point 2, which is nearly 1 million miles beyond Earth's orbit. This telescope's mission is to help answer the question...
Stage 2 LOX float has started.
To help answer the question, what is the universe made of, by exploring the cosmic mysteries of dark matter and dark energy. It will create an unmatched 3D map of the universe by observing billions of galaxies across 10 billion years of cosmic time across more than 1/3 of the sky. The mission today was named after Greek mathematician and founder of geometry, Euclid of Alexandria. And since the density of matter and energy are linked to the geometry of the universe, the mission was named in his honor. The spacecraft today was built by the European Space Agency, or ESA, with contributions from the Euclid Consortium and NASA. In fact, over 3,500 people from 21 different countries were involved in making today's mission possible. After launch, Euclid will have a month-long commissioning phase while traveling to its final destination. After 2 months of performance verification, it will then be ready for its science operations to begin. ESA will need some time to process the data, but is anticipating sharing the first images with the public in the fall. In just a few minutes, we'll be joined by members of the ESA team to talk more about the mission, so stay tuned. At T-minus 15 minutes and counting, we're well into propellant loading on the vehicle. Both the rocket and spacecraft are healthy. Weather is green and looks great over there in Florida, and range is ready to support liftoff at 11:12 a.m. Eastern Time. We do have a backup opportunity tomorrow at the same time if we don't lift off as scheduled today for any reason. Our Falcon 9 rocket and the Euclid payload rolled out to the pad from the hangar yesterday and went vertical a couple hours later. Now looking at the very top of the rocket is the payload fairing, or just fairing for short. And there you can see it on your screen. The fairing is made up of two composite halves that come together to encapsulate the Euclid payload in order to protect it from aerothermal loads, heating, and contamination during ascent. Now you might be able to tell that the fairing halves supporting today's mission are brand new. Once we reach the vacuum of space, the fairing halves will separate and we'll attempt to recover them for potential future use using our recovery vessel, Doug. Now below the payload fairing is the second stage, which is responsible for taking our payload to its drop-off orbit in space. Today's launch marks the first mission for SpaceX taking a payload with a final destination of a Sun-Earth Lagrange Point 2 orbit. Right under the second stage is the inner stage, which connects the first and second stages together, in addition to housing the Merlin vacuum, or what we call the MVAC engine, on the second stage. The inner stage is equipped with pneumatic pushers that allow stage separation between these two stages during flight. Once separated, the second stage will continue on its journey in space, while the first stage will start making its way back to planet Earth. And speaking of the bottom two-thirds of the vehicle is what we're referring to when you hear the term first stage. You may also hear it being referred to as the booster. The bottom of the booster is equipped with 9 Merlin engines, and that gives us the 9 in the name for Falcon 9. These 9 M1D engines are used to accelerate the vehicle through the Earth's atmosphere and into various orbits in space. You may be able to tell by the soot on the first stage, but this is the primary part of the rocket that gets reused multiple times. The first stage supporting our launch today is flying for its second time, having supported the AX-2 mission just about 6 weeks ago. After liftoff and stage separation, we'll be attempting to recover the booster using our drone ship, which you can see there on your screen, a shortfall of Gravitas, which is currently stationed in the Atlantic Ocean. With liftoff currently set at 11:12 a.m. Eastern Time, let's learn a little bit more about today's mission.
In 1915, Albert Einstein astonished the world with his general theory of relativity. It described the behaviour of the entire universe based on the matter and energy contained within it. The theory sparked the modern discipline of cosmology and the hope that we would finally understand how the universe came to be. But in recent times, the effort to define what the universe is made of has given us a very big surprise. Visible stars and galaxies make up less than 5% of the universe's total matter and energy. Beneath this visible layer is a mysterious celestial realm, consisting of shadowy particles and unknown energy fields. For decades, astronomers have puzzled at their nature, calling these elusive substances dark matter and dark energy. ESA's Euclid mission will go in search of the answer to the fundamental question: what is the universe made of? A European-designed mission, Euclid is built and operated by ESA, with contributions from the International Euclid Consortium and NASA. ESA selected Thales Alenia Space to lead on building Euclid, with Airbus Defence and Space providing the telescope and payload module. The telescope and scientific instruments form the heart of the mission. Together, they will observe billions of galaxies over more than 1/3 of the sky. Producing record quantities of data, Euclid will enable scientists to draw a precise map of the universe across space and time. This will allow researchers to investigate the effects of dark matter and dark energy on the apparent shape of galaxies and on their motion and distribution over immense distances. In turn, this will help reveal the true nature of dark matter and dark energy. The spacecraft and data communications will be controlled from ESA's European Space Operations Centre in Darmstadt. To cope with the vast amounts of data Euclid will acquire, ESA's EdgeTrack network of deep space antennas has been upgraded. These data will be analysed by the Euclid Consortium, a group of more than 2,000 scientists from more than 300 institutes across Europe, the US, Canada and Japan. Understanding the elusive nature of the universe has drawn astronomers throughout history. It remains one of the most challenging investigations in modern science, but Euclid is up to the task. The Euclid mission is a quest into the unknown, a mission to shine a light on the dark side of the universe.
Euclid is SpaceX's first mission to a Sun-Earth L2 transfer orbit, also known as the Sun-Earth Lagrange Point 2. The Sun-Earth L2 transfer orbit is nearly 1 million miles beyond Earth's orbit and a most ideal orbit for space-based astronomy because telescopes in this orbit, like the James Webb Telescope, can keep the Sun, Earth, and Moon behind them while being close enough to transmit large amounts of data to Earth and receive solar power from the Sun. Now, in order to get the rocket and payload into any orbit, the rocket has to not only go up really fast, but it also has to go sideways. As we ascend, we tilt the engines, and that turns the rocket horizontally. To help demonstrate this concept, imagine firing a cannon from a really high mountain. The cannonball will arc, and then good old gravity will pull it back down to Earth. As you increase the power, the cannonball will arc and land farther and farther away. Eventually, if you could continue to increase the power, the cannonball will end up in free fall around the Earth. Basically, gravity is pulling down on the cannonball, but it's going so fast that it never hits the ground. This arc that constantly misses the Earth is called an orbit. Falcon 9 effectively does the same thing as the cannon in this example. It provides enough power and horizontal velocity to the spacecraft on board the second stage that the spacecraft is placed in orbit around the Earth. You'll be able to see this today by watching the orientation of Falcon 9 after liftoff. The rocket will go straight up until about T plus 10 seconds,
internal power.
At which point we begin that shift in orientation by gimbaling the engines so Falcon 9 can go horizontally really fast. So be sure to look out for that after liftoff. With about 7.5 minutes left until liftoff, we are joined by NASA's Megan Cruz and ESA's Director General Joseph Aschbacher over at Kennedy Space Center in Florida. Hey, Megan, how's it looking over there on the East Coast?
Hey, Jesse, welcome everyone to Florida and NASA's Kennedy Space Center, where just behind us, we are waiting to see Euclid launch on a Falcon 9 rocket right off the launch pad behind us. As you said, joining me this morning is Joseph Aschbacher, the Director General of the European Space Agency. Good to have you here this morning.
Glad to be here every time.
Yeah, I love that you're here. And yeah, just talk to us about how Euclid's launch that we're about to see in a few minutes comes on the heel of a great year for you guys at ESA.
ESA had really a fantastic year. We just came out of a ministerial conference in November last year, plus 17% more budget, many new projects, many new activities, so quite fascinating. We have selected 17 astronauts. Some of them will fly from here into space. We have just signed an agreement with Axiom. We're having 5 astronauts in training right now at the Astronaut Center. We have launched JUICE earlier this year. JUICE is an amazing mission which fits very well with Euclid, which is looking at habitability of the icy moons of Jupiter, something quite unimaginable, just as crazy as Euclid, dark matter, dark energy, which is really amazing. So we have a lot to do. We have a space summit coming up towards the end of the year, where we want to raise the profile of space in Europe to top-level politicians and to see what Europe needs to do to really be a strong space power, also to our partners in America.
Right, and in order to foster that, the space industry, I mean, one of the reasons you really want to do that is to also address a global issue that we here at NASA really care about as well.
Oh yes, we do. We have many satellites that look at our planet. Climate change is the largest problem on our planet for many decades to come, if not centuries, and we need to do everything we can from space. We have the Copernicus program, we have Meteor program, we have just launched MTG-1 last year, fantastic images that just came out, and we really make sure that we use our space assets to the best of humankind, and climate change is one of our big concerns. And one element which we just launched is not only on ground that we want to see at climate change, also in space. And I'm about to really initiate a zero debris charter where we would like to encourage people worldwide to not pollute our orbits. That means if you put a satellite up, you put it down at the end of its lifetime, and that's a new initiative we are doing.
Great. And any words for all the scientists that are hoping to really learn a lot from this Euclid mission?
Oh, the incredible science will come out. I'm pretty sure some Nobel Prizes will be won based on this data. This is really a fascinating mission. I'm so happy. I thank thank my community, my member states, industry, NASA also as a partner, and all the contributors to this. And thank you so much for this contribution.
Well, congrats to you, and I can't wait to see Euclid launch.
Thank you.
Thank you so much. Back to Hawthorne.
Thanks, Megan. We are about T-minus 4 minutes and 40 seconds away from liftoff. And at this point in the countdown, the clamp arms are going to begin to open up beneath the fairing, and then the transporter erector will begin to retract away from the vehicle in preparation for launch.
Retract has started.
And there we heard that call out. And you can see the clamp arms just below the fairing there on your screen. Those should begin to open shortly here. Once those are fully open, then the transport erector, or what you heard called the strong back, will retract away from the vehicle. And there you can see the clamp arms opening up there. Again, once those are fully open, the TE will begin to slowly retract away from the vehicle. And it is very slow and slight, but the TE is now beginning to move away from the vehicle. At this point in the countdown, both the first and second stages are nearly fully loaded with 1 million pounds of kerosene fuel and liquid oxygen. Both first stage and second stage should finish prop loading about a minute apart from each other. First stage finishing up at T-minus 3 minutes, and second stage at T-minus 2 minutes. At T-minus 60 seconds, Falcon 9 will be in startup. Now, what that means is the rocket's autonomous internal flight computers will have taken over the launch countdown. Just in light the Merlin 1D engines for liftoff. The Euclid payload continues to be healthy, and the Falcon 9 team is tracking no issues on the rocket. Currently, both the vehicle and payload are healthy.
Stage 1 lock flood is complete.
And we're looking good for an on-time liftoff at 11:12 a.m. Eastern Time. So let's send it back to Megan over there in Florida.
Hey, Jesse, you can start to feel the energy here at NASA's Kennedy Space Center. We're just behind us. We are waiting to watch the Euclid spacecraft launch atop of Falcon 9, again, on the launch pad right behind us. So with me now is Carol Mundell. She is ESA's Director of Science. Really great to have you here today.
Hi, Megan. Great to join you.
So talk to me about why studying dark matter, dark energy, why is that so important to understanding our universe?
Yeah, sure. This is one of the biggest unsolved problems in modern physics. So we actually think we understand only 5% of the universe, with the matter that we see, galaxies, stars, planets, ourselves. So 95% of the universe, dark matter and dark energy, is still a mystery and enigma, a huge frontier of modern physics that we hope this mission will actually help to push forward.
So then how do you go about detecting things we can't see?
That's a great question, and of course this sense of darkness really comes from the fact that dark matter does exert gravitational pull, so we see the effect of it. We look at galaxies and they spin too quickly for the number of stars and the amount of gas they have. We look at the clusters of the universe and we see too much mass. And so we don't know what fills that mass. It might be exotic particles. It might be that we've got our equations wrong. And on top of that, our universe is expanding. But the really big mystery for modern physics, that expansion is accelerating, so it's actually getting faster and we don't know why. Our equations don't tell the whole story, and so what this mission will do is it will map all of that out to 10 billion years back in history and hopefully tell us the answer to the mystery of life, the universe and everything.
So then really quick, when do we expect to get this data back to start really analyzing it?
Yeah, so this is a 6-year mission, and the first 3 months of the mission will actually be calibrating the data because this is a huge feat of engineering technology. We have very, very precise images across all of the extragalactic sky, and then scientists around the world. We have 2,500 scientists in Europe and in the US across 9 data centers. We'll analyze these data all the way through 6 years. So our final cosmology answers will come at the end of the 6 years, but we'll do lots of exciting science along the way as well.
Carol, thank you so much. Very exciting.
Thank you.
Thanks, Megan. Thanks, Megan. We are just under 1 minute. Falcon 9 is in startup, and we are just waiting for the final go for launch.
LD, go for launch.
And great news, all systems are go for launch of Falcon 9 and ESA's Euclid Space Telescope.
T-minus 30 seconds and counting. T-minus 15 seconds and counting. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition, liftoff.
vehicle is pitching downrange.
Falcon 9 has successfully lifted off from pad 40 and throttled down to prepare for max Q, which is coming up at T plus 1 minute.
Power and telemetry nominal.
1 minute and about 12 seconds. Max Q is the highest amount of aerodynamic pressures. That's the largest structural load that the vehicle will see on ascent. We throttle down those engines just to pass through max Q, and then we'll throttle them back up once we pass through that period.
Falcon 9 is supersonic. Maximum dynamic pressure.
And great news, we have passed through max Q. You're getting some excellent views there on your screen. Next up, we have a few events happening back to back. That will be MECO, stage separation, and SES-1. MECO is main engine cutoff, and that's where we'll shut down all 9 of the M1D engines to slow the vehicle down in preparation for its next event, which is
MVAC chill has started.
Stage separation. And that's where the first stage separates from the second stage. Right after stage separation, the first stage will begin its journey back to Earth for landing on our drone ship, a short fall of gravitas. And during that time, stage 2 will continue on its journey with that third event, SES-1, or second stage engine start 1. And that is where the single Merlin vacuum engine will light up and propel the second stage along with ESA's Euclid spacecraft to orbit. In addition to these 3 major events, the fairing halves will separate less than a minute after SES-1, so keep an eye out for all of those events coming up here in just about 15 seconds or so. Again, coming up, we have MECO, stage separation, and SES-1.
Main engine cutoff. Stage separation confirmed. MVAC ignition.
Some really cool views of MECO stage separation, and on your right-hand screen, you can see that the MVAC engine has ignited.
Both vehicles are following nominal trajectories.
On your left-hand screen, the grid fins on the first stage are deploying, and in about 15 seconds or so, we should have fairing separation. And a very cool view from the ground.
Fairing separation confirmed.
And there you can see on your right-hand screen that the fairing halves have deployed. Now, as I mentioned previously, both fairing halves are brand new and are now making their way back down to Earth and will be recovered by our recovery vessel, Doug, today. It is T plus 4 minutes into today's mission. And in order to complete today's landing, the first stage has 2 more burns left. Next up is the entry burn, and that's where 3 of the Merlin 1D engines will reignite. This helps to slow the vehicle down as it re-enters the upper parts of the Earth's atmosphere. Now, that entry burn is coming up in about a couple minutes from now, and that entry burn will last about 20 seconds long. And what you're looking at on your screen, on your left-hand side, is a view from the first stage vehicle, currently making its way back down to Earth, which you can see in the background. And on your right-hand screen is a view from the second stage looking aft at our MVAC engine.
Acquisition of signal, Bermuda.
That entry burn is coming up here just about a minute and a half
Both
from now.
vehicles continue to follow nominal trajectories.
And good call-outs there. On the bottom of your screen, you can see the speed and altitude of each vehicle as well. And on your left-hand screen, you can see 2 of the 4 hypersonic grid fins that the first stage has. Those grid fins help guide the vehicle as it makes its way back to its landing zone. Again, today we are scheduled to land on a shortfall of gravitas, currently in the Atlantic Ocean, waiting for the first stage vehicle. And on your screen, you're getting a great view from the second stage with the MVAC there and the Earth looking amazing in the background. We're just about 20 seconds away from the entry burn on the first stage vehicle. You may see some white puffs on that first stage. That is nitrogen gas puffs for attitude control.
Stage 1 FTS has safed.
And there you can see the engines have reignited on the first stage on your left-hand screen. This is the entry burn with 3 of 9 M1D engines reignited. And you can see that those engines have shut down. That concludes the entry burn for the first stage. Now we do have one more burn for the first stage vehicle as it attempts to land on our drone ship, and that is the landing burn. It will just be a single engine, the Center E9 engine reigniting, and that is enough thrust to help slow down the vehicle to enable it to touch down on our drone ship. Now, during the first stage landing burn, the vehicle will be landing for its second time.
Stage 2 FTS is safed. Stage 2 terminal guidance.
The vehicle will be landing for its second time today, and just before the landing burn begins, we will also have SECO 1 on the second stage. That is second engine cutoff 1. That's where we'll shut down that MVAC engine on the second stage. This is the first of 2 burns for this mission, and that is coming up here in just a few seconds, followed by the landing burn about 20 seconds after that. There you can see that the MVAC engine has shut down and the landing burn has begun on the first stage vehicle.
Expected loss of signal, Cape. Nominal orbit insertion.
What an incredible clear view of Falcon 9 touching down on a shortfall of gravitas. This landing marks the second successful landing for this particular booster and marks our 204th overall successful recovery of an orbital class rocket, including both Falcon 9 and Falcon Heavy first stages. We also heard the call out for SECO 1 and confirmation of good orbit. So with confirmation of a successful second engine cutoff and first stage landing, we are going to be in a coast phase until just before the second relight of our MVAC engine on the second stage, which will be followed by payload deploy. So sit tight and we'll see you back here around the T plus 17 minute mark.
booster landings never ever get boring, do they? That was what a clear view that was. Well, Euclid is truly on its way now. Exciting and pretty emotional stuff. It's really great watching a rocket launch with all the people that really it matters for. Remember, you can ask your questions to the experts that I've got. Just hashtag Ask ESA anywhere on social media, and I'll try and get those questions answered. We've had a few coming in already. So while SpaceX take a break, we'll keep their data on the screen so that you can keep up to date with the telemetry there. We'll have that second stage ignition in about 5 minutes. So let's hear from Florian Renk, who's joined me, and he's the head of mission analysis. Welcome to the show, Florian.
Hi, Matt.
So how long have you worked at ESOC?
Well, at ESOC, almost 15 years.
15 years? Oh, wow. OK. And how long have you been involved with this Euclid mission?
Euclid for almost a decade.
Wow.
Yeah.
So these missions, they just don't happen overnight, do they?
No, definitely not.
Now, I did promise the viewers earlier that I would explain what on earth L2 was. So can you give us just some layman's rundown about an orbit around L2? What on earth does it mean?
Yeah, L2 is a position where there is nothing, but it's a special point in space where the gravitational pull of two bodies combines. So you have to imagine a line from the Sun towards the Earth and extend that by another 1.5 million kilometers out. And this is where the gravity of both bodies is just the right thing that you can rotate with them. So we will stay on that line. And actually, we can fly Euclid around that line.
So, yeah, it's flying around. So is there any special reason why you would go to this L2?
Yeah, Euclid is an infrared telescope, so it's sensitive to heat. And essentially in infrared, our Earth is a huge light bulb in space. So that we can make the measurements we want, we have to get away from the Earth. And therefore, this L2 point is beautiful because it's far away. We've got the Sun, Earth, and the Moon in one direction. And it's also a good distance where we can still transmit sufficiently high data rates to get all the data from Euclid down.
Yeah, and we've got right behind you, we've got your beautiful animation of how Euclid gets to its beautiful, I mean, it's just a great animation of how it gets into orbit there. So is it particularly good for the science as well?
Yes, because since we orbit around that Sun-Earth line, we are in permanent sunlight. And that's actually crucial for the mission because we want the spacecraft to be thermally stable, absolutely stable, because we stare in one direction for a very long time. And if something would contract because it's getting colder or so, it would cause a jitter, and then the image would get blurry and we wouldn't be able to make the signs.
Yeah, so it's a bit like if you're focusing on a camera, you're making your lens shorter or longer.
Yes.
And obviously you don't want that to happen when you're taking
Absolutely
a very long exposure. Yeah, it's really interesting. Are there any other spacecraft that use L2?
Yes, there's a couple of spacecraft. The most well-known one is, I guess, James Webb and Gaia, the ESA spacecraft, which is there.
Yeah, and when I've mentioned this, people say, "Oh no, what happens if Euclid crashes into James Webb? What's the chances?"
Very, very small. The orbits are super large, so the amplitudes of the orbits are in the 100,000s of kilometers, so it's wider than the orbit of the Moon. So the probability of meeting James Webb would be very, very, very small.
OK, so luckily there's no chance of that whatsoever.
Not really.
Whatsoever. So we've got to get out to this L2. So how on earth does that happen?
OK, the Falcon 9, which we were just seeing, is putting us essentially on the perfect trajectory to do that. So we almost don't need any propellant to make it to L2 because that is done by the launcher. Although we have to do a little bit of corrections there because it's a technical system. It's not as super accurate. So 2 days into the mission, or 1 day into the mission, we will fly a small correction maneuver where we correct for the inaccuracies of the launcher. And then it takes roughly 30 days to make it to L2. And we have 2 more maneuvers where we correct for tiny errors of that maneuver and also for the solar radiation pressure. And once we are at L2, there is a very tiny maneuver every month just to keep it in that orbit.
Yeah, because some of these L points, you can either stay in them indefinitely, can't you? Get trapped in them, but this isn't one of those.
This isn't one of those. It's one of the collinear ones. The triangular ones are the stable ones, but they are too far away.
Yeah. So what else does the Falcon 9 have to do to actually get Euclid into position? Is there anything special that it does in this particular flight?
Yes, and this is actually the flight phase we are in right now, which is a drift phase, because, you know, the Earth has this 23-degree tilt of the equator, of its rotational axis, and to get a nice launch window for Euclid, we have to be in the equatorial plane for the second burn. And this is what's happening right now. So the upper stage drifts from Cape Canaveral towards the equator, where the upper stage engine is ignited again. And that balances our launch window over the year so that we are not getting too far out of the ecliptic plane. And that's, besides the right speed that the Falcon is giving us, also the right direction.
Yes, and that's happening right now, isn't it? That is what where we're right at.
Exactly,
it's
that's
drifting
the phase.
across, and we're waiting for this second burn. So we keep calling it L2. So what does it? You've actually changed my mind on this. What does the L stand for in L2?
There's two things you can name them. So the first word is libration point, because it's kind of an equilibrium point where you've got a nice balance. The second one is Lagrange point, which you will also hear quite often, because Lagrange found all the 5 libration points, or Lagrange points.
So they get called Lagrange points. So, but you call them librations. Why is that?
Because Leonhard Euler found the collinear ones, the first 3 ones.
Yeah, everyone who knows me knows that I love a good Lagrange point, but I think I'm going to start calling them libration points because I feel so sorry for good old Euler. Yeah. So I mean, you know, it must be great fun working on a mission for this long to actually work out all these orbits. So that's, you know,
for the Euclid mission.
That's, you know,
if you're just joining us, liftoff occurred
so we
at
are going to go
11:12
back to
a.m.
SpaceX
Eastern
in a
Time
second
Space Launch Complex
to go and
40
have a look
in
at this
Florida.
second burn. So
After
we're going
liftoff,
now.
we also had successful main engine cutoff, stage separation, ignition and shutdown of the second stage, bearing separation, and first stage landing. Now, coming up shortly, we'll have our second burn of our MVAC engine on stage 2 prior to payload deploy, which basically means that we will relight and shut down the second stage engine for a second and last time. Now, SES-2 is coming up here in just about 10 seconds or so. Again, SES-2 is second stage engine start 2, and then we will shut down that MVAC engine about a minute and a half later.
MVAC ignition.
There we heard that call out, and you can see on your screen that the MVAC has reignited. Again, this burn will last about 90 seconds, and it will be the last burn of stage 2 before we deploy the payload. As a reminder, the Euclid payload is still attached to the second stage at this point and will be heading to a Sun-Earth Lagrange point to transfer orbit. And that is about 1 million miles beyond Earth's orbit. Now we should have SECO-2 coming up here in a few seconds. That is second stage engine cutoff. Again, will be the conclusion of the second and final burn for this mission.
MVAC shutdown.
We've just had SECO-2.
Nominal orbit insertion.
There's that call out. We just had SECO-2 and confirmation of good orbit. So with successful second engine start and cutoff, we'll join you live to cover payload deployment in about 20 minutes. So we'll see you in a few.
Wow, it's really exciting stuff. It's those images are absolutely brilliant, and everyone's buzzing in here. So while we wait for the Falcon 9 and the spacecraft itself to coast into a position for separation, I've been rejoined by Elena Majoreno, our spacecraft engineer. So tell me a little bit about the history of the construction of Euclid.
The industrial consortium, you mean? So the industrial consortium was starting about end of 2012 when the telescope responsible Airbus Toulouse was selected, and then immediately after, around April, June, the prime contractor Thales Alenia Space was selected for I would say, driving the industrial consortium. The selection of all the subcontractor started immediately and was quite a long process because we procure a significant number of equipment around all Europe. And it lasts around 1 year. And the process of design was going on in parallel. The critical design review, that is the final point in which the design is frozen, was in May 2018, sorry. Yeah. 2018. And in parallel, the industry were starting the production of the flight model that were delivered, and they will start progressively be integrated into the structure of the spacecraft. We had the final mating of the telescope and the service module in the 2022, and then the environmental test campaign started, and the spacecraft arrived in Cape Canaveral when the launch campaign was completed in around the end of April, beginning of May. So it was a very long process, a lot of people, 80 company, 140 contracts, and around 20 country involved. So.
Yeah, I mean, we've just been watching, I believe all your colleagues, they're right by the right by Euclid itself, and it's really extraordinary to actually see it to scale, indeed, isn't it, to actually see what it looks like compared to the scale of a human. So how do you feel when you look at your spacecraft when it's like that? And knowing that it's on its way now.
Super proud, of course, and it's beautiful. I mean, it is beautiful. It's really beautiful. And I started the very beginning of the procurement of the industrial consortium, 2013, and I followed the procurement, the integration, and the testing of quite a number of units on the platform, and then yes, was really exciting, and being able to be there in the different moment, to see the spacecraft growing, arriving at the final stage, go on through the testing phase successfully, and now be there almost in its final position to go to L2 is really, exciting, amazing, and it's great.
We're all kind of overawed with emotion from watching it.
And as I said, a lot of people around Europe was involved, so it was a pleasure, and also was great to work with all these people, very brilliant engineer and technician.
Yeah, I mean, just to point out to viewers that was sped up footage. The Thales Alenia people don't work that fast, but it actually marks the 10th anniversary, doesn't it? This launch of Thales Alenia signing that contract. Was that a coincidence, or?
Absolutely, it was a great coincidence, because we were supposed to launch with Soyuz from Kourou, and then for the reason we know, that was a discontinuation of the Soyuz launcher, so we were looking for a different launcher, and we start evaluating the possibility to launch with Falcon 9 last year in July, indeed, and was a quite quick process, because we were able to understand that was feasible, and then we went super fast. We speed up the process that normally is taking a couple of years, and we arrive at the date of the 1st of July. But that's really an amazing coincidence.
What a great coincidence, yeah. So Euclid is expected to handle just vast amounts of data, isn't it? Yeah. It's like, well, it's mapping the universe, you know. It's an understatement, it's a massive amount of data. So what kind of things do you have to do and take into consideration to handle all that data?
Yeah. So the instrument will produce around 850 gigabit per day. That, if you compare with the nominal capability of an hard drive or a memory stick, you can think that's nothing. But we have to think about that we have to store all the data on board, because we don't have a continuous contact with the Earth and the ground station. We have only 3 hours, 15 minutes of daily contact, and the distance is one, as I think Florian explained, in L2 will be about 1.5 million kilometer distance. So we have to store all the data in a mass memory, and then we will transfer the data in these 3 hours through a K-band antenna to the ground station. We will use file, and it's the first time we are transferring file, and for that reason also the ground station will have been updated to be compatible with Euclid, and also for the transmission in the K-band was selected for the high throughput that the bandwidth was granting.
Yeah, and of course we're mapping the universe, and these are very, very bright, very, very dim objects that we're trying to capture. So what was, in terms of precision pointing and things like that, how did you overcome those challenges?
Yeah, exactly for coping with this very stringent pointing requirement, there was a new development. So there is a new equipment that was taught exactly for that. That is the fine guidance sensor. That is a sort of evolution of the star tracker that are commonly used, but is more powerful in the sense that is able to detect objects and stars that have higher magnitude, so they're fainted star, and the information collected by the FGS will be used by the algorithm of the AOCS to define the pointing of the telescope for running the observation.
Yeah.
Of course, sorry.
Yeah,
I was going
it's about time that we need to go over and check in on the main control room. Thank you so much, Elena, for giving us just a glimpse into just the unbelievable amount of work that must go into something like this, like a decade of work. It's truly remarkable. So thanks very much for sharing that story with us.
Thanks.
So I think it is time that we went over to the main control room now. So how is it going in there, Tiago?
So, Matt, no, we are flying. And we are waiting for the spacecraft separation coming in some minutes from now. So at the moment, all the team is expecting separation of the spacecraft.
Can you give me a little rundown of the who's who in there?
Sure. So in this room, we've got several teams who are responsible for several different things in the operations. So we have what we call here the front row. We got the flight control team with experts who are responsible for the operations of the spacecraft. So we've got several positions dedicated to the communications, the onboard computer, the power, the thermal control, the orbit control. They're all managed by the person near mission, who is the spacecraft operations manager. He's in its position monitoring the activities of the front row. So that's our flight control team. Then here at the back, we've got what we call the back row. The back row is composed also for several positions of teams. We've got here the software coordinator position, who oversees all the systems and the software that is used to control the spacecraft. We've got the OMs, the operations managers, who are responsible for all the ground stations and all the infrastructure, the communication links and everything that we use on the ground, in our ground infrastructure, to do the operations. And we've got here, then on this side, we've got there at the back, Luis, who is our project representative, who is with Elena and the team that built and developed this spacecraft and managed the industrial contract with Airbus. And here at the back, we've got the flight director, who oversees all the activity and the conduct of operations in here. So he's the leader of this system, of the team of teams, I should say, and who is the conductor of the orchestra, if you like.
So, Tiago, we've actually got a question for you that's come in on the hashtag AskESA. It's Arnold Mural from Instagram asks, what's the weirdest pre-launch superstition? So do you have any superstitions or launch rituals before launch?
Superstitions, okay. I think everybody will have theirs. We have traditions. We have our launch briefing the day before launch. We had it yesterday. We have our shot, the photo shot of the entire mission control team. That is very nice. And we have, of course, one of the biggest traditions here is that in the door of the main control room, we've got all the best wishes cards from all the flight control teams in the center who wish well for Euclid in the flight.
That's absolutely awesome. So many things happening in the background, and the day is so complicated. How do you prepare for a day like that?
Well, in a word, practice. So we've been sitting here in this configuration with these teams several times. I think 20 times we did in what we call the simulations campaign. We come here, we practice all the scenarios, nominal and off-nominal, as we call them, that we are running today. So what we see today, in principle, is already the case with the countdown. That was very good. We expect that everything is as we've seen before several times, and therefore you know what to expect, and the team is prepared for all the possible things.
Thank you very much, Thiago. That's awesome. So if you've just joined us, we're in Germany, here in the heart of the control centre where they actually fly the European fleet of satellites. And you can join in at home by sending me your questions using the social media and the hashtag AskESA, as you just heard. Keep them coming and I'll try to get them answered. And as you can see, I've been joined by a theoretical cosmologist, Guadalupe Canas Herrera. I hope I haven't butchered it too much this time. Welcome to the show. And how are you feeling after that launch?
Super emotional, but also extremely grateful and thankful for everything that has done so far, so we can actually have a telescope now in space.
Yeah. So how long have you worked on the project?
So I joined the Euclid consortium back in 2018. I did my PhD preparing for this mission, and yeah, 5 years.
5 years, yeah. So it must be super exciting to see that launch. Yeah.
Wow.
Yeah.
Unbelievable.
Yeah. And so how long have scientists like you been working on this Euclid launch?
So in 2011, ESA designed the Euclid consortium to be the scientific collaboration in charge of the exploitation and the analysis of the data. So more than a decade now, yeah.
Yeah, so I mean, in my mind, it's almost like the scientists only get to work when you get this big bundle of data. So obviously, but you've been working with them for over a decade, the scientists, and you've been working for 5 years now. So what exactly have you been, what is your role in the Euclid?
Well, you need preparation in exactly the same way that all the engineers and the fantastic team that we have here at ESOC, they have been exhaustively preparing for this moment. We also had to prepare for getting ready to analyze the data. Yeah. So we've been constructing pipelines. We were verifying that actually with the current scientific requirements, we are able to provide back what it is required from us, the goals of the mission, which is analyze the nature of dark energy and dark matter.
Yeah, so I mean, so there really is decades of work, isn't it? It's like from the beginning to when this all wraps up, it'll be several decades.
Yeah. A lot of years of work, but also rewarding work, we hope.
Yeah, and of course you're really young, and so this is going to be a big chunk of your career as well, isn't it?
Yeah, it was. Euclid has been part of my scientific career so far, and I expect that it will be part of my next decade.
Yeah, so that's what things like this launch must mean just so much to you.
Yeah, for us it means the beginning. Also, like the beginning of testing everything that we have been testing, and getting ready to treat ourselves with data.
Yeah. Well, one question that has come in from Twitter, I've seen quite a lot, is the images that we might get from it, because it's a survey telescope, isn't it? And therefore we're building a big map or something like that. But will we have like lovely images like James Webb gives us or Hubble gives us? Is it that kind of telescope? Will we get that?
Definitely. The quality and sharpness of Euclid image is fantastic. And actually, we hoped that after commissioning, we can provide to the society with these magnificent pictures so they can test it on their own. The quality is similar to Hubble, but the quality of Euclid is that it's able to provide us way more, wider pictures.
Yeah. So, I mean, at the end of the Euclid mission, what kind of final product do you hope to have?
The final product is the 3D map. So this is the ultimate goal. And by comparing this 3D map with our theoretical model, we expect that we can put constraints on the cosmological ingredients, the dark cosmological ingredients that we have in our universe and their nature.
Yeah, so what is so special about this 3D map, and how does it relate to geometry and dark matter and dark energy?
So the thing is that this 3D map shows how a structure has formed in our universe so far, and also because we are measuring the positions, the 2D positions of galaxies, but also the shape of galaxies and the distance, because nothing can go faster than the speed of light. Looking at at these distances of galaxies is like looking at the past. So we can actually have a cosmic history view of how our universe have evolved over the years. And this is essential to test our theoretical models.
Yeah, so we've actually had an Instagram question from Christmas, Crimson or something like that on Instagram, and it cuts to the chase, I think, and it's how will Euclid be able to detect dark matter?
Yeah, so we are not a mission that will detect directly dark matter. We rely on the indirect effect that this dark matter has on the images of our galaxies by measuring the distortion on the shape of galaxies, which is really subtle. But if we have many galaxies, we can actually average over so many galaxies that the statistical certainty increase. We will be able to trace where matter is distributed in our universe. And as we know that just a tiny percentage of this matter is baryonic matter, we are potentially seeing where dark matter is.
But it is a very different problem to, say, dark energy as well, isn't it?
Yes, so it was a really poor choice of names, I have to say. Yeah, so dark matter, it is called dark because it doesn't interact with light, so it means that we cannot see it. The name dark energy is referred purely on the base that we don't know anything about it. So yeah, they are significantly different. So the idea behind dark energy is that it is this unknown substance, that it is driving this accelerated expansion of our universe. As I said, we call it dark because we don't know what it is. But do you remember that I was mentioning these distances to galaxies that are gonna able to give us like some time view of the evolution of the universe? This is gonna be crucial to measure this accelerated expansion and potentially constrain dark energy.
Yeah, I've got another question actually from hashtag #AskESA, and that's what are the potential implications or discoveries that scientists anticipate from Euclid mission, and how might they impact our understanding of the universe as a whole? And that was from Astro Mishra.
Yeah, well, we have high goals for the Euclid mission. We definitely would like to test, to actually obtain these 3 maps. So we know we have like a more exhaustive knowledge of how a structure has formed in our universe so far that will allow us to test so many different theories, also understand better this accelerated expansion of our universe, so that we believe that it is driven by dark energy, or potentially there is like a better modified gravity theory that is allowing us to explain that. But also, yeah, we can potentially also say something about the origin of the universe as we are tracing where matter is, or even say something about some funny little particles that are called neutrinos. So yeah, Euclid will have some constraining power on that too.
And I'm going to ask my own personal question. We've got there's the crisis in cosmology, the Hubble constant being different.
Yeah.
Do you think it might actually solve that?
Yeah, but I don't know if solving, but definitely we'll have something to say in here.
More information about that.
The more information, the better, because we will be able to say, in which direction statistically we are aligned. So the Hubble tension is basically some tension that we have in the measurements that we obtain of the Hubble parameter. That is basically a measurement of the expansion of the universe. Either we obtain it from measurements about the origin of the universe, like really deep in the past, or nowish. It seems that there is a discrepancy that we have to test experimentally. We need Euclid to put more light on this.
Yeah, well, thank you so much for giving your enthusiasm about the science of Euclid. It's an awesome mission, and you must have such good. I wish you such good luck with the in the future of
fingers crossed.
Fingers crossed. Yeah.
Yes.
So thanks very much for joining me. So I think it's about time that we check in with Susie Jackson now, the manager over at New Norcia, the other side of the world in Australia. There we go. So welcome back, Susie. It's not long now before your big dish. In fact, it's completely changed direction. Is going to be directly pointing at our Intrepid spacecraft. Can you give us a little bit more detail about how this works and what to do next, and what the next 10 minutes might look like?
Yeah. So first of all, you'll see the dish behind me will start to rise. We'll hope for acquisition of signal from the spacecraft pretty much straight away. We're tracking both the launcher vehicle, the top of the Falcon 9 rocket, in S-band, plus we're also tracking the spacecraft itself, so that we'll be able to see everything that's happening as things come over the horizon. And as soon as we've got telemetry, we'll start steering the dish here to lock onto that signal, and we'll be able to get the signal down from Euclid. And then once we get up to about 5 degrees up in the sky, we'll be able to start talking back. So we'll turn on our transmitters and we'll start sending the very first commands, telecommands, up to the Euclid spacecraft, so that we can get the testing underway and get things going.
So thank you, Susie. It's always a pleasure to hear from you, and please stay put because we'll need you back. So we're edging ever closer to our big milestone of acquisition of signal. It's in about 4 minutes or thereabouts. But before we get there, there's the Euclid spacecraft must leave the vehicle and ready to go solo for the rest of the 1 million mile, 1.5 million kilometre journey. So we are going to go back to SpaceX and watch that happen, hopefully.
Again for the ESA Euclid launch. We've had a great mission so far, and we have just one more major milestone left in our mission, which is payload deploy. Built and operated by the European Space Agency, or ESA, with contributions from NASA and the Euclid Consortium, the Euclid spacecraft will be operated from European Space Operations Center in Darmstadt, Germany. It will explore dark matter and dark energy, which combined is known to make up 95% of the universe as we know it, and create an unmatched 3D map of the universe with time as the third dimension by observing billions of galaxies across 10 billion years of cosmic time across more than a third of the sky. Now, deployment is coming up here in just a few seconds.
Euclid spacecraft separation confirmed.
And there you can see the Euclid payload drifting away from Falcon 9's second stage. With that confirmation, we'll bring today's webcast to a close. Today's mission marked SpaceX's 243rd overall mission to date and 44th mission of this year. We want to thank the European Space Agency for entrusting us with today's mission and all of you for joining us. If you're interested in following the Euclid mission further, tune into youtube.com/ESA for more. And be on the lookout for the first images from the Euclid telescope later this fall. Thanks for tuning in, and we'll see you again soon.
For those just joining, we are in the control room in Germany, and that was just incredible footage.